So what we would like to do today, I will continue with the same topic of the economic load dispatch problem, but today we will have a little glimpse of basic optimization techniques, okay, which will be required to solve this economic load dispatch problem. So we will have a little bit of math review, we can say, a little bit of math review, which would be helpful for understanding this economic load dispatch solution. So these things we covered in the last class, and we actually started this with this formulation of economic dispatch problem. So our target was basically to minimize the cost, and as we said, the cost we are interested in for this topic is the fuel cost, okay, or the running cost, or the instantaneous consumption, fuel consumption cost for the thermal power plant or the thermal power plants. So to start with, we assumed that we are not considering the generation limits. Okay, so we are assuming that the generator can provide sufficient amount of power, and there are no transmission networks, so no transmission losses are included here in the problem formulation. Later on, we will see how the inclusion of these generator limits and the losses modifies the solution. Okay. So this is our objective function, the first one. CT is the summation of all the costs, okay, starting from I equals to 1 up to M, where M is the total number of generators, and each cost functions are function of the generation of its own, okay. So that means the cost function for generator number 1 is dependent only on its own generation, okay. So the ith generation is linked with the fuel cost of the ith machine. So there is no coupling, okay. There is no coupling between the jth machine and the ith cost, ith machine's fuel cost. So they are decoupled. So this is our objective, and we are saying that there is one equality constraint, okay. So we have to look for the minimum of this solution, okay, of this cost, keeping in mind that I have to satisfy the demand plus the losses, although for this topic, okay, to start with, we are considering that there are no losses. So P losses would be 0 to start with. So only consideration equality constraint would be summation of all the generation from the available power generating units should be equal to the demand. So then we mentioned about the unconstrained optimization and the optimization with equality constraint, and there we mentioned about this Lagrange multipliers, okay. So how we are going to use the Lagrange multipliers in solving the economic load dispatch problem? To understand this from mathematical perspective, okay, what is the physical significance or interpretation of this Lagrange multipliers? We will take, we will go away from this slide a little bit for the time being, and then we will come back here. So we'll start a new slide. Okay. Okay. Can you see this, the new slide, optimization slide?
Yes, sir.
Okay. So we will start with a little overview of the optimization techniques. So let's start with this, and then we'll again move back to our original discussion of economic load dispatch. Okay. So our main target for today's part of optimization, we will focus on the physical significance of the meaning or interpretation, physical interpretation of the Lagrange multiplier. Okay. So to start with, we'll focus on why is it needed, why do we need optimization? This has been answered already, okay? We could be looking for some sort of, let's say, maximization of some profit of an industry, or minimization of some cost in an industry, and or we could also be trying to look out for some trade-off, okay? For some trade-off. Let's say you are looking for some quality in the product. At the same time, you are looking to minimize the cost. So that could be one example of the trade-offs, okay? Because this is a kind of a trade-off decision making, because if you're looking for increased quality, okay, better quality product, then you have to spend more money. But at the same time, if you want to have this at a reduced cost, that means you are trying to save money, okay? So you are in a dilemma, okay? So that's why that kind of problem could be treated as a trade-off decision making process in optimization. So for maximizing profit or minimizing cost or some blended flavor of those two, this is why optimization is needed. What are the types? We will go through those. And how do we reach at the optimal solution? There are different sorts of methods. Basically, it is not a new domain. Okay? It's not a new domain of discussion. The optimization has been done for long. Okay, for long. So there are some classical methods which were adopted, historically adopted and successfully adopted, but at the same time, none of the methods are actually, we can't say this is the best, okay? So the researchers are always looking for some better methods time to time, okay? So that's why the recent methods came into picture, and we'll also focus on those as the course moves on. So we can categorize the methodologies of the solution methods for the optimization into these two major blocks. One is the classical methods, another one is the recent methods. So why we need optimization, I've already mentioned. You would either looking for the minimization of some cost function, or let's say you are trying to minimize the input energy, okay? That means, in other words, you're trying to make higher efficiency machine, okay? You are trying to reduce the energy consumption of the system, of any industry or of any process. You are trying to reach somewhere, okay? You started from somewhere and you are trying to reach there in the quickest possible time. So you might be also looking for quicker time, okay? Quicker time to reach or complete some process. Then probably you are looking for some increased profit out of a business. Probably you may also look for some better efficiency out of a machine. And as I mentioned earlier, you could also look for some sort of trade-offs, and there could be many other examples, okay, in this list. So I have listed here a few of them there, but there could be many other examples. You can fill up the list. There are some scenarios. I will not go through all of these. I will pick some of these, okay. So in the scenario, you will see different colors, okay. Some blue colored words, some red colored portions, and some green colored portion. The blue colored ones, let's go through the statement first. There are 320 yards of fencing available to enclose a rectangular field, okay. So these are some of the key informations required for conducting your optimization. First of all, you have the information that the size of the field, okay, the size of the fencing would be rectangular shape, and the numerical value is also provided. So you have two information. One is the size of the field, another one is the amount of fencing which is required. Okay, you have 320 yards of fencing and you want to enclose a rectangular field. So how should this fencing be used? So that means how you are going to utilize these 320 yards to create fence around this rectangular field, okay? So that what is your target? The enclosed area is as large as possible. The enclosed area is as large as possible. So the green colored portion basically gives you the idea whether you are looking for maximization or minimization or some sort of trade-off, okay? So the green colored portion gives you the idea whether it is a maximization problem or a minimization problem. Here it is explicitly mentioned, but sometimes it might not be the case, okay? The information you have to extract from the problem statement sometimes, but here it is explicitly mentioned, okay? Enclosed area, we're looking for the fencing size, okay? Fencing size, how should this fencing be used so that the enclosed area is as large as possible. So you're looking for some area maximization, okay? Maximizing the area. So out of these 320 yards, remember the unit, okay? It is length, unit of length. So you have a sheet, let's say you have a sheet of 320 yards, sheet of some materials, okay, plastic materials or some sort of materials. You have a long sheet of 320 yards. Now you have to cover the area where the area shape is rectangular. Okay, so rectangular area has to be fenced using 320 yards long sheet, and you have to cover the largest possible area. Okay, so what are your constraints? Anyone? What could be your possible constraints? I have talked about the objective function or optimization function. The optimization target is you have to enlarge the area as much as possible. So this is a maximization issue. So now, whether it is a constraint problem or an unconstrained problem, you have to look at the statement again. What about this 320 yards? What information does it give? Anyone?
It's the limitation of 320 yards.
It is the one sort of constraint. Yeah, it is the periphery. Okay, you can say it is the periphery. Okay, it's the periphery. So 320 yards. So this is a constraint, and this is the periphery of what? Of a rectangular. You can cover this 320 yards periphery using for this rectangular area. Okay, so you can mathematically formulate. Okay, mathematically formulate what is the area. Area would be your cost function. Okay, because you're looking for the enclosed area. So the cost function, mathematical formula for the cost function would be the area of the rectangle. Okay, area of the rectangle. Let's say one side is A, another side is B. So this is your simply area. Okay. So if I want to write it in, let's say A multiplied by B. So this is your cost function. Okay. Let's say this is your cost function F. You are trying to maximize this. So you are trying to maximize F, where F is the multiplication of the two sides of the rectangular field. One side is A, another side is B. So this is the area. Now, what is the constraint? Anyone? What would be the formula?
2 into A plus B equal
2
to
into A plus
C.
B. So 2 into A plus B. So this is your formulation, 2 into A plus B. So this is your constraint. The periphery.
Should not it be less than or equal to 320?
No, we are okay. That is not explicitly mentioned. So we are treating it as well. We are going to utilize all the available, sheet, because I have already bought it. So I am going to utilize every part of it. Okay, I'm not going to spare any of that 320 yards. Okay, so that's why I'm putting equal sign. That's a good question. That's why I'm putting equal sign. So we treat it as we are going to utilize all.
Because it is said, how should this fence? Okay.
Yeah. So this fencing should be, you are going to utilize all the 320 yards. These 320 yards you are going to utilize, and then you are looking for the largest possible area. So actually you are looking for the values of A and B in such a way that maximizes this and that satisfies this. Okay, that satisfies this. Okay. You are looking for the largest possible area here. Okay. So this is your problem statement, and this is how we are going to extract informations, and we are going to formulate the mathematics behind the different scenarios listed here. Okay. So similarly, you can form the optimization problem here for any other statements or any other scenarios. Okay. Let's say if you have, let's say example number 3, given a list of cities. Okay. So you are given, your information available is a list of cities. Okay. So you have a list of cities. Let's say you have 4 or 5 cities list. And you also know the distances between each pair of cities. Okay. Each pair of cities is also available. So the question is, what is the shortest possible route? So is it a maximization or minimization problem?
Minimization.
It's a minimization problem, because we are looking for the minimum possible or shortest possible, or we are looking for the quickest route possible. How we are going to find out that shortest route. So this is the condition. We can say this is the constraint. Okay, so the constraints are basically colored in blue. The constraints are colored in blue. The objective is colored in green, and the other informations are colored, necessary informations are colored in red. Okay, this is the background behind the color coding in all these examples. So what is the constraint? The constraint is you have to visit each city exactly once, and you have to return to the original city. Okay, so let's say we start from Dhaka, and you have to cover Khulna, Barishal, Chittagong, Rajshahi only once, or exactly once. Okay, not more than once and not less than once. So this is equally, you can say equality constraint. You have to touch every city once and only once, and then you have to return to Dhaka. So what is the shortest possible route? Okay, given you have the city's name, okay, Dhaka, Chittagong, Rajshahi, and so on, and you know the distances between each pair of cities. So this is one example of finding out the shortest distance, okay, shortest path between your source and destination. Okay. So similarly, there are other examples. You can try out each of those, okay, on an individual basis, or you can have some group discussion on these, and you can try to extract informations regarding the objective of each of the problems and the constraints of each of the problems. Okay. Any question here? So actually, I have tried to find out different sorts of examples. Okay. There are many other examples, of course, you can find anywhere of optimization problems. Now let's look into the types. Types could be unconstrained, as we already discussed in the last class. That means you might have no constraints to fulfill. Okay, you are free to choose the values of your solution variables. You are free. You have the freedom. In that case, you only have the objective function. You don't have to satisfy any constraint. This is type 1. Type 2 is constraint examples. You may have equality constraints, as we saw in this case. Okay, 320 yards was our equality constraint, and you may also have inequality constraints. Okay, as we move along, we will give probably the examples will come up one after one. So now let us see how we are going to treat the unconstrained optimization. Probably this is already covered in some of your mathematics course earlier, isn't it? Unconstrained optimization, maxima, minima. Anyone?
Yes, sir.
Yeah, sure. So in that case, this would be simply a little, simple review. So unconstrained optimization. So you will have an optimization function. Okay, f of x, you have some function to be optimized, and you don't have any constraints. So there are no restrictions on the values of the variables. There are no restrictions on the values of the variables. You are free to choose the values. Then for finding out the optimum value, the sufficient condition is that you calculate the gradient. Okay, you calculate the gradient of your optimization function or your fitness function, and you equate it to 0. Okay, so the first symbol here is the gradient symbol, and f and x could be scalar, could be vector. F could be a function having dependent on multiple variables, or a vector of variables. So that's why the boldface x means it is a vector. Okay, boldface x means it is a vector. So if I want to calculate the gradient of a function having vector variables x1, x2 up to xn, then this is how you are going to calculate this. Okay, so let's say your function f, your objective function f, is a function of n number of variables in x. Then you are going to calculate calculate the gradient of this fitness function. Let's say die fx of die x1 and so on, and those will be calculated along the first, column. That would be a column vector. Okay, so that's why it is being put as a transpose. So that would be a column vector. So for an example, simply I have included the example of, let's say, yeah.
To a transpose metric.
Transpose means whatever elements are here, they would be simply, they have to be transposed. Okay, the transpose is here. In this case, it is used to save the space, nothing else. In general, you should have written it like in single column, diFx over dx1, here diFx over dx2, and so on. Okay, it would be going like this. But just to save the space, I have put them in transposed form. Clear?
Yes, sir. Understood. Yes.
Because why it is being written in this fashion? Because x is treated as a column vector. So your x elements are not in a row, okay, in a single row, rather they're in a single column, x1, x2, x3, x, like this. It goes from top to bottom. So that means it is a single column vector. So when you calculate your gradients with respect to a column vector, the resulting elements should be also along the column. Okay, is that okay?
Yes, sir.
On the other hand, if x was, or if x were a row vector, okay, along this direction, then there would have been no transpose. So here I'm considering my x elements are along this line, okay, along the columns. That's why the elements, the gradients calculations should be along this column, the first column.
Sir,
yeah.
How can I understand that x is column vector or row vector?
Yeah, x is column vector or row vector. In general, they are, when you try to formulate this sort of problems, x's are in general formulated as a column vector, not as a row vector. Okay, as a row vector. But it doesn't matter. Even if you calculate, or even if you treat x as a row vector, it doesn't matter. Your solution vector would be along this line, and the calculations later on would be affected. Okay. By this, what I mean, I will show it in the next slide. Okay. Okay. It doesn't matter whether you take it as a column vector or as a row vector. Just you have to follow the pattern strictly throughout your calculation. If you consider x as a row vector, then you have to treat it as a row vector throughout your calculation. Don't intermix row and column. Sometimes row, sometimes column. Okay, so it doesn't matter.
Yes.
Let's say for a single variable x, we are trying to find out the optimum, and this is an unconstrained optimization. So we are looking for f of x, a sine function from 0 to, basically the x-axis is your pi, okay, 0 to 2 pi, this is in radian, and the y-axis is the magnitude. So if you're looking for the optimum value, so you have to take the gradient and you have to equate it to 0. So simply calculate the gradient of f of x. So what you get, simply get the first derivative of sine x with respect to the single variable x. Okay, we don't have a vector of variables there, you have a single scalar x. So it would be cos x equal to 0. So what are the probable solutions or feasible solutions? Feasible solutions are pi by 2 and 3 pi by 2. Why I have limited the solutions up to this point? Because I don't want to look beyond this range. Okay, I want to limit my solutions, or I want to check my solutions from 0 up to 2 pi. For this sort of periodic function, actually it will continue up to n pi by 2. Okay, we all know it. But for specifically for this problem, I want to limit my analysis starting from 0 to twice pi here. Okay, this is in radian, twice pi. And in the y-axis, you have the magnitude. So clearly we can see the optimums are either at this point, okay, at this point, or at this point. Okay, I'm talking about optimum. I have not mentioned whether it is a minimum or a maximum. I'm only talking about we have some, okay. So we are only mentioning whether it is a maxima or a minima. Okay, so the first derivative doesn't guarantee you whether it is a minima or a maxima. It only gives you information whether it is an optimum point. Okay, whether it is an optimum point. It could be either a minima or a maxima. So at pi by 2, what do we have? We have a maximum value of the function. At 3 pi by 2, we have a minima of the given objective function, which is sine x, and which is 3 pi by 2. So these are the feasible or probable solutions to the problems, optimum points. Now to check, the next question is, now if I am looking for specifically, whether looking for the information, specific information, whether it is a maxima or a minima, then we have to go for the second derivative condition. Okay, second derivative. The first derivative doesn't give me enough information to identify whether it is a maxima or minima. It only gives me the information that it could be a minima or it could be a maxima. To differentiate between maxima and minima, I have to go for the second round of derivative, and I have to evaluate that expression at the points of interest. So the point of interest means these points. So the x values, probable optimums are this, at x equal to pi by 2 and at x equal to 3 pi by 2. So I have to check the second derivative expression at these 2 points. Okay, so let's go and check. So I have calculated the second derivative. So simply my first derivative was cosine of x. So if I take the double derivative, so it will get minus sine of x. So this is what we get. Okay, simple. Now I have to check the sign. Okay, where should I check? I should check at the points of interest, or the probable solution points. So my probable solution points are pi by 2, x equals to pi by 2, and x equals to 3 pi by 2. So I put the values one by one. So my expression is minus sine of x. So at x, I put, instead of x, I put pi by 2. So it is minus sine pi by 2. So it is minus 1. So at x equal to pi by 2, I get the second derivative value as negative. The solution or the decision is, if the sign of the second derivative is negative, you have reached the maxima. So it satisfies our answer from the graph. From the graph also, you can see that it is a maximum point of the f of x function. It is a minus sign for the second derivative. Similarly, if we put x equal to 3 pi by 2, you get a plus sign. So it is here. Basically, the sign is positive. So you are basically talking about a minimum. Okay. Now the question is, if it is a positive or a negative, it's fine. You can either decide it is a maxima or a minima. Decision is done. What would happen in the third case? If there is any case, let's say the sign is neither positive nor negative, rather the value comes up as 0. What do you think? What should be the decision? This should have been done in your earlier math course.
Sir, it's like an inflection point where it
Yeah, excellent.
not
This is the
neither minima or
It
maxima.
is neither minima nor maxima. That is a point of inflection. Okay, thank you. So those who have forgotten, please go back and check what is a point of inflection. But this is condition number 3. This might also happen, that if the solution could be 0 and you have reached the point of inflection. So for multivariable functions, we have till now we have discussed a single variable function. Our function was f of x equals to sine of x. Right now we are looking for a multivariable function, still unconstrained optimization. What we have to do, we have to go through all these steps. Okay, so first of all, again, we have to take the gradients. We have to take the gradient with respect to all variables. Let's say you have x1, x2, x3 up to xn. You have to calculate the gradient with respect to all variables and equate all of them or each of them to 0 separately. That condition has to be satisfied. Okay, so that means di f over di x1 should be 0, di f by di x2 should be 0, up to di f over di xn. All of them individually should satisfy this condition. Okay, this is the necessary condition. First order optimality condition means the first derivative. Okay, then you have to solve the resulting expressions for all unknown variables. Okay, that means if you have n number of unknown variables, you expect n number of equations, so that n equations, n unknowns, you can easily solve them. So all these solutions from this second step would give you the candidate solutions, okay, for all possible maxima or minima. Still you are not sure whether it's a maxima or minima, but at least you are sure that it is guaranteed that they are optimum points. Next, to find out the specific information about the points, whether it is a maxima or a minima, again you have to go for the second derivatives, and now whatever information you get, that is a matrix, and that matrix is known as the Hessian matrix. We call it H, capital H, okay? The Hessian matrix. We'll take one example and show how we go through all these steps, okay? So nothing to worry. So then we evaluate the H matrix as we did for the single variable case for the sin x function. Again here we have to evaluate the H matrix at each of the candidate solutions. Remember, we might have several solutions, okay? As we had for the sin x case, we had two solutions, okay? Pi by 2 and 3 pi by 2. So similarly here, for the multivariable case also, we might have several probable or candidate solutions. So you have to evaluate the H matrix at each of those solution points. Again, if H is positive definite, because now we are not talking about scalar value, rather we are talking about a matrix. So if the matrix is positive definite, definitely positive, then the point is a minima, but this minima is a local minima, and there is also the concept of global minima, okay? If the H is negative definite, the point is a maxima, again only guaranteed is the local maxima, okay? How do you ensure whether it is a positive definite or negative definite? We'll come to that point with the example, next example, okay? If there is only one maxima or one minima or one maxima, okay, then that is the global point, okay? So that means you have found the best optimum position possible, because you only have one solution, okay? So you don't have to decide between several solutions. You have only one solution, and you have found that it is either a maxima or a minima using these two conditions. So let's say you have found that point is a maxima, so that means that is a global as well as the local one, okay? That is only true if you have only one solution, only one candidate solution. Otherwise, you have to evaluate the cost function at each of those candidate solutions, and then you have to, by looking at the values, you have to find out which one is the global and which one are the locals, okay? So let's take the example. So this example, three variable example. So x is a vector now having three variables, and this is the cost function which we have to optimize. So what is the gradients? Again, the gradients are simply because this is a three variable function. So simply you get the derivative or the gradient calculated, partial derivative calculated and equated to 0. So simply you go for di over di x1. So this would be 2x1, this would be 0, 0, this would be x2, 0, minus 8, and the others will be 0 equals to 0. So similarly, you can calculate this. There is nothing special here. So similarly, you calculate with respect to x2, look at the expression, and you simply take the partial derivative with respect to x2, equate it to 0, and you have three variables, so you have to do these gradient calculation for all these three variables, and all of them should be equated to 0 individually. And then the next step, you solve them, okay? By solving them, I mean you are looking for the candidate solutions. How many unknowns? You have three unknowns, okay? You are looking for the values for x1, x2, and x3 such that this f expression is optimized. So your unknown variables are three: x1, x2, and x3. How many equations you have? Three equations, okay? You see equation number 1, equation number 2, equation number 3. If you go through all these equations, you find only the presence of any of these three variables, okay? There are no more unknowns there. Only either x1, x2, or all of them are probably there is a mistake. I have to correct this. So this would be, oh no, this is okay. Let me check. 4x2 plus x1 plus x3 minus 16. So this should be 6x3 plus x2 minus 30 plus, okay, probably there is some mistake. I have to correct this, okay? But you can do it, okay? You can do it. So if we do it, what would we get? We will get 6x3 from here. You will get x2, and there is a mistake, I think. This x3 should not be here. So this is the mistake, okay? Please correct it. I will correct it in the later version. Then if you put them into this matrix form, okay, you can simply form the matrix, okay? So you see, actually this is a typo mistake problem. In the matrix formation, this x3 is not there. So if you form the matrix, you take the constant terms to the right hand side. So you can simply form the matrix, okay? If I take this, the next slide, just for your easiness of understanding. So what you get, you see, simply I'm formulating the matrix here. So my unknowns are x1, x2, and x3. So I start with x1. So the coefficients, I simply take the coefficients, 2x1 plus x2. There is no x3 here, equals to 8, okay, like this. 4, okay, then x1, 4x2, and there is probably, there is another mistake. 210144. Okay, I think I have to check it, okay, but I'm just giving you the solution. Probably during the copy paste process, probably there was some mistake, okay, I'm sorry. But you can simply plug the values here, okay, simply plug the values from your solutions, plug the values from your solution, and when you calculate this, finally you will come up with this solution, okay, 325. I will fix it and I will post it in the revised slides, okay, I will fix it. So this is how you get the matrix formulated, and then simply take the inverse of this, take it to the right hand side, and then you get the result, okay? So because you have only one solution here, okay, these equations are simply linear systems of equations, So you don't expect multiple solutions as the solution of this system, okay? So only one candidate solution, which is 3, 2, and 5 respectively. And then you calculate the Hessian. Okay, you calculate the Hessian, and when you calculate the Hessian, that means you are taking the second derivative, and these are the expressions for the Hessian entries. So you have to calculate, like it was di f over di x1, you have to calculate di square f over di x1 square, di square f over di x1 x2, and di square f over di x1 x3, okay, and so on. So you take the coefficients, although probably the coefficients here I have to check back again what was the problem. So the final solution you will get is this, okay, is this. And now to check the positive or negative definiteness, you have to calculate the eigenvalues, okay. We talked about eigenvalues. We talked about how to find out the positive and negative definiteness. So talk about the eigenvalues. Then these are the conditions. If the minimum of the real part of eigenvalues of H is greater than 0, that means, in other words, if all of your eigenvalues are positive, okay, all of the eigenvalues are positive of the Hessian matrix H, then H is definitely it is a positive positive definite matrix, okay, definitely positive. H is definitely positive, and that means you have reached the minima. That candidate solution will give you the minima. On the other hand, if all of the eigenvalues of the matrix H are negative, less than 0, then you have reached the maxima for the candidate for the objective function f. Okay, so for this example, simply when I calculated the eigenvalue of H, simply using MATLAB, you find that these are the 3 entries of the eigenvalues. All of them are positive, strictly positive. So the obtained point is a minima, as the H matrix is positive definite. Now, can you tell whether it is a global maxima or not? Oh, sorry, a global minima or not? It is of course a local minima, but is it also a global minima?
Yes, sir.
Yes, why?
Sir, একটাই তো solution. Only
Yeah,
one solution.
you only have one solution, you only have one candidate solution. So this is the local minima as well as the global minima. Thank you. So to find out the value, numerical value of f of x, you simply plug in these 3, 2, and 5 there in your expression of f of x, big expression. This expression of f of x, you plug in the values and then you find that it is 2. Okay. So this is how in the unconstrained optimization case you can solve the problem. Now we go into a little more trickier issue. If along with the objective function, at the same time, if we have to satisfy the constraints, so we start with the equality constraint, which is less involved, mathematically less involved, okay? But the inequality constraint is a little bit more involved. So today probably we will be able to finish the equality constraint, okay? We will use, we'll take help of some graphical tools, okay? Graphical tools to make us believe, okay? Make us believe, we should say, that whether the Lagrange is a meaningful concept or not, okay? The Lagrangian multiplier, whether it is a meaningful entity or not. Have you gone through this topic earlier, the Lagrange multiplier? What is the physical interpretation in any of the courses? Do you remember?
No, sir.
Not yet. Okay, probably when I start, probably if it is covered, then probably you would recall. If not, then no problem, we will cover it. So now in this case, we have a constraint optimization. We have some equality constraints. We are going for maximizing the function f of x. This is our original objective, okay? The given objective, subject to some equality constraint. So whenever you see some equal sign in the constraint expression, that means it is the equality constraint. Now to solve this, we define the Lagrangian. How do you formulate the Lagrangian? We simply take the original objective function f of x at first, then we add the equality constraint function with the multiplying factor lambda, which is known as the Lagrangian multiplier. It is, I mentioned it in the last class, I am again mentioning it here. This is lambda transpose, just to match the dimension of this expression with the remaining portion of the equation, okay? So if you have multiple expressions, okay, vector, multiple expression, g1, g2, g3, g4, for each of the equality constraint, we have to consider a different or separate lambda, okay? So if you have, let's say, 3 g expressions, g1, g2, g3, you have to take lambda 1, lambda 2, lambda 3, and in that case, this expression g of x and this lambda t are to be placed in such a way that the dimension here matches with the remaining portion of the expression. That's why you have to put the lambda in transpose form, okay? In general, we consider that all the vectors in general are represented in along a column, okay, along a single column. So transpose means it would be along the row, along a single row when I take the transpose of a vector, okay? So what is the necessary condition? Simply you have to take the gradients of this new objective. We are calling this as our new objective, okay? This is the original objective, but this is now the new objective. And now let's say if it is a maximization problem, then the necessary condition for a maxima is what? So we have, because we have two variables, actually x could be a vector and lambda could also be a vector. So basically you have to go for the partial derivatives, because you could have x1, x2, x3, lambda 1, lambda 2, lambda 3, and so on. So the first condition is this, and at the same time you have to also satisfy this, okay? Because you have two different sets of variables, x as a vector of variables, lambda as another vector of variables. So you have to take the partial derivatives separately and equate them to 0, okay? This condition has to be satisfied simultaneously. Simultaneously, you have to satisfy this condition. Okay. So let's take one example of an objective function having two variables. Just for simplicity, it is a nonlinear function because of the presence of this square term and the multiplication of between these two variables. You have a constraint. Now, what would be the shape of this constraint? Geometric shape.
A circle.
Circle.
The circle, unit circle. Okay, it's a unit circle. A unit circle. Okay. So the constraint is a unit circle. You are trying to maximize this expression for different values of x1 and x2, but you are also looking to satisfy these equality constraint, which is basically a unit circle. So we follow the step number 1. We define the Lagrangian. So what we do, we simply take f of x plus, you take lambda transpose, because we have only one g here, so you could also write simply lambda. Okay, simply lambda, and then you write it in this fashion. That means you take the constant term first, and then you take the other mathematical expression to the other side. And because you remember it was g of x equal to 0, okay, you can make this 0 in two ways. Either you can take the 1 in the left side and make it 0, or you can do the reverse fashion. Writing this g of x in this fashion actually helps us in calculation. That's why we are taking it. Okay? But you could also go for x square, x1 square plus x2 square minus 1 equal to 0. There is no harm in doing that. But representing in this manner basically helps in calculating the lambda values. It helps to keep the lambda values positive. Okay? There is no other special benefit. Just to make lambda positive, we write it in this fashion. There is no other additional advantage. So there is nothing special in representing, taking this to the right hand side or bringing the 1 to the left hand side and making it to 0. There is nothing special. So now take a look at the geometrical interpretation or the physical interpretation. What is this Lagrangian actually? Let's look at the contours of our fitness function. Okay. So I will elaborate each of these curves slowly. So the green curve is basically the circle. So you see the unit circle. In whichever direction you go, it covers. This is my center, 0, 0. Okay, with a small red dot at the center. And at each direction, it covers 1 unit. Okay, so this is a unit circle represented by this expression, x square plus y square equals to 1. And then there are several contours of my objective function, x square y. Basically, this in our case it is x1 square into x1 square plus x2 square, but in general it could be x square plus y square. Okay, and this our fitness function is x1 square into x2 equals to c. That means each of these contour lines basically gives me a fixed numerical value, scalar value for this expression x square y. That is to say, if I am moving along this line, I have a fixed value along all the points for different values of x in the x-axis and different values of y in the y-axis. I will get same value for different combinations of x and y along this contour. Let's say that is C1. Okay, C1. Similarly, if I move along this contour, then I get C2. Okay, then I get C3. Means different constants. Is that clear? What these contours mean?
So that means any 2 point, any value of x and value of y,
Yeah.
we have same C along the curve.
Along the contours, yeah, along these contours. Okay.
Yes, yes, sir.
So we have a fixed C. Let's say this is C1. Let's say this is 0.5, then 0.7, 0.8, like this. Okay. So at any points they satisfy a single value. So the values of x and y are changing, but the C remains constant along any of these lines. So along this line you have a certain C. Along this line you have another C. Along this line you have another C, and so on. Okay, clear? So this is the contours. But this plot is actually provided here for a certain limited values for x and y. Okay, so I have plotted it for x equals to 0 to 1. So x equal to 0 to 1 means these contours, these ranges are given for the contours actually. Okay, these ranges, the upper ranges are given for the contour lines. So X is here from 0 to 1. So starting from 0 to 1, I have taken different values of X, and Y is also taken from 0 to 1. So you see the other values of Y and X are actually not included. And between these two ranges, only these contours are satisfied. So that's why they have been included here. If I change my limits, okay, if I change my limits of X and Y, then let's say if I take X from -1 to 0, -1 to 0, then the contours are simply mirrored, okay? You get the mirror image because you see the X limits are the same, Y limits are the same here. X limits are basically mirror image, okay? It was 0 to 1 here in the left hand side, the right hand curve, it is -1 to 0. So simply the mirror image will come. Is that clear? The circle remains same. I'm not bothering with the circle. I'm only showing you the different contour lines that would be obtained simply by manipulating or changing the limits of X and Y. Okay, you may have contour here, you may have contour here, you may, I mean, if I consider 4 different quadrants for this circle around the center point, then you can simply choose your XY limits and you can play with the contours. Okay, clear?
Sir.
Yeah.
Sir, when we are taking the mirror image of X, X limit, so then C will be same or different?
No, C will be different. C will be same. Okay, C will be same. Why C will be same? Because you see, if you look at the expression, you are changing X. Okay,
Yes, sir.
Y is still the same. The polarity or the sign of this expression only depends on Y, not on X. Is that clear?
Yes, sir.
So Y, if it is minus, only then it will be different. If it is minus here, if it is plus here, only then you may expect a different value of C. X, it is irrespective of the polarity because it is squared. I am only taking the mirror image along X. Okay. So you can say the mirror image is there, but the C values should remain the same. Okay.
Yes.
So if I combine both these, okay, if I combine, let's say if I combine them, what would I get? I would get X from -1 to +1, right? And Y, because I haven't changed Y, so Y would be still from 0 to 1. 0 to 1 means from above this 0 point, from 0 to 1, okay? So I will be focusing on this. If I combine both of these, what is expected? Anyone?
The combination of two?
Yeah, I will have something here and I will have something here, right?
Yes, sir.
So simply combined, so this is what I will get. Clear?
Yes, sir.
So the C will remain same, but the X values are different. Okay, that's why they are being shown on different zones. Although C are same, let's say this C and this C are same, but the C magnitude of C, the value of C are not actually explicitly mentioned here. So the location of the contours are different based on the value of X. Okay, because these are the X from 0 to 1. So these are the X from 0 to -1, and these are the X from 0 to 1. So these contours are being plotted here based on the X value and Y value, okay? Not on the C values. C values are implied that they will be having fixed value. So now, after all these contour lines and the graphs, okay, just a minute, okay? Please allow me some minute. Okay, sorry for the interruption. Okay, let's continue. So with all this information about the contours being present in different zones in XY plane, and the circle is still there. Now let us look, what was actually our target? Anyone remembers after looking at these contours? Again, I'm saying this x1 square, x2 is basically, you can also think it about x square y, okay? So don't get upset by looking at the different symbols. They are simply two variables here, x1 square, x2. Here it is x and y, all the same. So our target was basically to find out the maximum value of this x1 square x2 or x square y, whatever, where the x1, x2 values or xy values lie on this circle, right? Lie on this circle, because this is an equality constraint. So I have to look for x1, x2 values. I have to look for the maximum combination of x1 and x2, x1 square x2 basically, in such a way that it also lies on the circle, unit circle. Do you get my point? Any point, yeah, any point of the circle, any point of the circle or away from the circle is not satisfying this equality condition. Is that clear? Any combination of x1 square x2 which is not on the circle is not a valid or feasible solution or a candidate solution. This should be clear. This is why this is a constraint problem. Otherwise, I could take x1 equals to infinity, x2 equals to infinity, right? Simply, I could take the maximum value. What is the maximum value? Simply take infinite, x1 infinity, x2 infinity, that's it. But because we are constrained, we cannot go away from this curve. We have to stay on this curve. We have to stay on this curve. This is the constraint, equality constraint. So keeping this in mind, let us look at the gradients of the function, okay? Why we are looking at the gradients? Because remember, our condition said you calculate the gradient. Remember, these are the gradients. And you equate the gradient to 0. You equate the gradient to 0 with respect to x and also with respect to lambda. That's why we are looking at the gradient vectors on these contour lines. Okay, here I have taken both contours. Okay, by that I mean I have taken this contour on the left hand side and also these contours on the right hand side, and then I have plotted the gradient field. So at each point you see there is a direction and there is a magnitude. Okay, by larger arrow it is the magnitude, a smaller arrow is the smaller magnitude, and by the direction it is, you see the angles. Okay, it's different. At each point, you see different angles are being created. So the gradient field gives you two information. One is the magnitude of the gradient field. Another one is the direction of the gradient field. Okay, just a minute, please. Allow me some time. Okay, again, sorry for the interruption. Okay, so let's continue. So these are the gradients. Okay, at each of the contour lines, you can see there are gradients on each of the contour lines. Gradient fields gives you the information of the magnitude of the gradient and the direction of the gradient. That was about my function f. The contours of f are plotted with the gradients, and also these are the contours for the circles. Okay, although this is not required for this problem specifically, but I have shown how the contours will change. Okay, for our example case, the circle which is of interest, can you find out which one? X1 square plus y1 xy square. The one
The
which is
outer,
yeah, this one. You see, this is one. Okay, so this one is basically your x1 square plus x2 square equals to 1. But I have only shown how a different contour would look like and how the gradients are actually going outward. Okay, from the away from the center, the gradients are going outwardly. These are the circle contours, but we don't need this specifically for this problem. We only need the information of the gradient, okay? And our point interested, our circle which is of interest is basically this one, okay? Which is touching the point 1, unit circle. Here also it is touching 1, the unit circle, okay? So if I am looking for the gradients for both of my circle, that is the equality constraint, as well as if I am also looking for, the gradient at my fitness function or the objective function, then I have to combine them, right? And I have to satisfy the gradient condition. Simultaneously, okay, simultaneously. So let us see if I plot them together, okay. So here I have plotted the circle and also the gradients. Now I have to check, one condition number 1 is the gradient, okay. I have to calculate the gradient for my fitness function, and also I have to calculate the gradient for my circle. And also I have to satisfy the equality constraint, okay. That means my control line, okay, my control line should touch the circle. So to find out those points, let me highlight those points. Okay, let me highlight those points. Few of them actually. This is one point. Okay, you see, this is one point where my control line is actually intersecting with my circle, right? This contour and my green curve are actually intersecting at this point. This is one point where I have intersection. The equality is satisfied. Similarly, at this point, it is satisfied, right?
Yes, sir.
This point, it is satisfied. This point, it is satisfied. So there are several points where it is satisfied, right?
Yes.
But can you find out what is the maximum point? This point, it is satisfied. This point, it is satisfied. So if I'm intuitively, if I'm looking for that point, probably this is the point. You see, the control line will give me higher value than all these, than these, than these, than these, is along this control line, which is just touching, just tangential to my circle, okay? And there is also a gradient being calculated here. I will show you the enlarged view in the next slides, just to have an idea. Okay, if I superimpose the circle and the gradient fields, then they will touch each other. That means the circle and the control line, you have different control lines. Okay, any control line above this contour are infeasible, okay, because they are not satisfying any intersection with my circle, right? Any control line here are not satisfying the equality constraint. And any other contours below than this are having lower values of C, okay? This point, this point, this point. So the maximum point would be achieved when they just touch each other, and that is this point, okay? Because it is a maximization problem. If I have an enlarged view, probably, yeah, here you see, okay? Here you see. So this is my control line, and this green one is the enlarged part of the circle. So at this point, they will have simply touching point here between this circle and this control line. So this point basically here, this point, we will term it as my probable solution or candidate solution, okay? At that point, we will term it as x1m and x2m. That's the solution, okay? This solution would be obtained after I solve this and this, okay? How do you get that point? We solve this and this simultaneously, okay? Now the question is still there. Why Lagrangian? Okay, why this multiplier? How does it have any physical significance? Let us see. We are a little bit away from that. Okay. Now if I remove all the other unnecessary gradients, and if I only keep the touching point here, okay, the touching point. You see at x1m, x2m, I'm telling about, let's say this is our solution. Let's say this is our solution. If this is the solution, that can be calculated mathematically, right? You can solve those partial derivatives and you can find out explicitly this point. So let's say this is our point. At this point, what would happen? I have to calculate the gradient, right? Let's say the green one is my circle. The green one is my circle, and I have to calculate the gradient. So this is the gradient direction, okay? The green one, arrow, green arrow. And at the same point, I have to calculate the gradient of my control line, this line. So basically this line. So the blue one, let's say the larger one, is my gradient on the control line, the fitness function control line. Now, in general, these two, because the expression of these two curves are different, right? The expression for the circle is something like x square plus y square equals to 1, right? And the expression for the fitness function here is x square y, right? So they have different expression. So it is most likely that the gradient value calculated at their intersection point would have different magnitudes, but they should be aligned with each other. They should be aligned with each other, okay? Is that clear? Because they have different expressions here. This is circle expression. The blue one is x square y, our fitness function expression. I am calculating the gradient at a certain point. So the gradient would be, it is most likely that they would have different magnitudes. But of course, they would be aligned. They would be parallel to each other. Now, to represent this relation mathematically, what we need to do, what we are doing basically, we are calculating the gradient of the fitness function. We are calculating the gradient of the circle at a certain point. They most likely are not equal, but there could be cases that they are equal. There could be cases, okay? That is not impossible, but in general, mostly because their expressions are different for del f and del g, most likely they will have a different gradient value. So to represent their linear dependency, what is done? We simply multiply a lambda, which is identified by the mathematician Lagrange. Okay. So let's say this is 4 and this is 10. So simply you write 4 equals to 2.5 into 10 equals to 2.5 into 4. This is what this Lagrange means. It simply maps this gradient into this gradient and simply creates a scalar relationship between these two gradient fields at the point of candidate solution. This is why this is physically explainable, okay? The Lagrange is not only a mathematical concept, rather it is a physical concept, and this is how this comes, this lambda value comes in between these two gradients, okay?
Sir,
Yeah.
that means lambda is helping to align them together.
No, they are aligned. They are already aligned. Lambda is just to equate them. Because if you calculate, they are already aligned. Okay, they are already parallel. Lambda is going to equate them because you are going to write down equal sign. You are going to equating them. That's why lambda is required. Okay. But it is, I mean, it is not impossible that they are already equal. In that case, lambda would be 1. It is also possible that they are in different direction. They are 180 degree out of phase. In those cases, lambda would be negative. Is that clear? This is just a general representation showing a positive relation between the gradient of f and the gradient of g. Okay. This is how the scalar lambda comes.
So why they have to be aligned?
Why they have to be aligned? Because you are calculating, you are taking the zero gradient for each of them simultaneously. You see the curvature here? You see the curvature? Look at the curvature. Look at the curvature, okay? Let me draw another line just for your understanding. Let's say you are trying to calculate the value of gradient at this point, okay? At this point. I have to take a circle maybe. So at this point, let's say you are trying to calculate the gradient, okay? So what would be the gradient? Oh, sorry. The gradient would be somewhere along this line, right? What would be the gradient here? At this point, it would be somewhere along this line, right? I mean, if I take this direction at this point along this line, so the gradient would be along this line. Okay.
Yes, sir.
In each case, in this case, and in any other case, there would be a component of gradient, of one gradient on the other. So simultaneously, they are not providing you the minimum point. Never, they will give you the minimum point. If you check any other point, okay, any other point here, or here, or here, okay, any other point, they will not satisfy the gradient condition simultaneously. Okay, this is the minimum point, and at the minimum point, the only possibility of the gradient where it is minimum for this and also it is gradient on this, it is only possible when they are aligned, otherwise not. Okay, let's say if the curvature was different, okay, like this. Let's say if the curvature were like this, what would happen? Curvature for G is like this, then this would not be your solution. Your solution would be somewhere where they are intersecting here. And the direction of gradient would be different in that case also. Probably that would be, you would have two lines along this direction, okay? Two lines along this direction. So to satisfy the minimum point, for understanding this, you have to look at the condition. For satisfying the minimum point, or the optimum point actually, the first order optimality condition says that it has to be, what should I say, gradient on each of the curves simultaneously. That condition is basically mentioned mathematically here. Let me go to the expression. This condition will give you the relation between F and G, okay, F and G. And this condition will give you another relation. So the both conditions should be satisfied simultaneously, okay. Both conditions should be satisfied simultaneously. If you move away from this point, specifically for this example actually, if you move away from this point, both of the conditions will not be same, okay. They will have different directions. They will have different directions at the point which is away from the minimum. Only at the minimum it will be satisfied. Only at the minimum point this alignment would be satisfied, I should say. This alignment condition would be satisfied. And another case is that, in other words, you can also say you have to also satisfy the condition where the equality constraint is met. Remember, it is an equality constraint, right? So equality constraint means what? Your contour expression, contour numerical value of the contour should exactly match, equals to your circle. And at this point, they are not equal, right? Are they equal? No.
No, sir.
Are these matched? No. Are these matched? No. Only at this point they are matched. So if you have a single point, okay, you have a single point where two curvatures are being matched, if you draw the gradients, mathematically they would be parallel. Okay, mathematically they would be parallel. But as I say, there could be cases where they are exactly equal. There could be cases where they are of different direction. But of course, they have to be aligned. They have to be aligned. Now, to represent this alignment and to make them equal, we have to introduce this Lagrange multiplier. Okay?
Yes, sir. Thank you.
Yes, sir.
Okay. Hope it gives-
Sir.
Yeah.
Sir, we have another class.
Yeah, I know, because we were at a critical juncture of discussion, so I could not stop actually, sorry.
Okay, sir.
So please, I would like to stop here. I don't want to bother you for the other classes.
Sir, attendance?
Yeah, when you leave, please write down your IDs on the chat box, okay? We will continue with this lecture in the next class, inshallah. Okay, the class is over. Please give your attendance and thank you again for joining.
Assalamu alaikum, sir.
Wa alaikum assalam.
Assalamu alaikum, sir.